Hello, everybody. I'm going to make a quick video on derivation of time dilation, which is the basis of special relativity. The most important aspect of special relativity is that the speed of light is the same in all reference frames. In a vacuum, obviously, if it goes through a medium, there's the interference, but even that would be the same in all reference frames. So the speed of light is 3 times 10 to the 8 in all reference frames. So if you run at light, it actually doesn't appear to come at you any faster. Obviously, you'll shorten the distance, but its speed will not appear to increase. Remember, you are always still relative to you. So this is the outside reference frame. If somebody is watching you run toward this light photon, they will see you running to the right at some speed and the photon coming at your face. The U reference frame is where you are still and you are not moving relative to yourself, and the ground has a speed v to the left. So the ground is moving underneath you, and that might make it seem like the speed should also be added to the photon, but that's not the case. That it's actually the same exact speed, and what ends up happening is this photon has the same speed, but is now a higher frequency due to something called the Doppler shift that we'll talk about later and learn and do. Shows us the speed of things emitting light, that if it's shifted in frequency, we know that there's relative motion. So you won't ever see light go faster or slower. Another one is, okay, same thing if I'm holding a flashlight and I'm running at somebody. This is the outside reference frame, right? If you're running and you're holding a flashlight, this is the same, right? The U reference frame is this is just you still holding a flashlight, and I might as well write that. You're still relative to yourself, and the ground, once again, has a velocity v to the left. Sorry, I'm drawing this arrow pointing at that it has a velocity, but the velocity is backwards to the left, right? So the ground is moving to the left here. In my reference frame, if I'm running this way, the ground is actually running underneath me. In my own reference frame, I am still relative to myself, and then I just see the light coming out of the flashlight at the speed of light. But the outside reference frame sees light coming out of the flashlight at the speed of light. Kind of crazy. And if I run at somebody, they'll see a higher frequency. If I run away from somebody, they'll see a lower frequency, but they will see the same speed no matter what the reference frame. So that's step 1. Step 2 is this. If I have point A and point B on a train, in the train's reference frame, the train is never moving relative to itself. and we have some distance d here. And let's say we shine a flashlight from point A to point B. Now, I really realize it doesn't matter whether this is vertical or across the floor like we did in class. It doesn't matter. As long as this distance is perpendicular to the direction of motion, which will be to the right, it's all good. And you might say, does gravity affect light? It does, but it doesn't affect its speed, right? So, or at least not yet. I don't know, don't overthink it. The point is, we don't want to assume that. Just assume that it's a straight path. If you want, actually, I think bird's eye view is better just to take that out, just because there are small gravitational effects that are real. I didn't mean for that to be confusing. We'll explore that later. I think bird's eye view is where it's at anyway. So bird's eye view. So it's all relative. In the train's frame, you're not going to see a speed change even locally due to the gravity. But let's just have it go sideways. Bird's eye view, going from A to B. Distance d, it's that. So distance is the speed of light times the time. Right? Great. So the time is the time inside the train. So the thing is, if I am now an outside perspective, the train has moved. Now, in the smallish amount of time, the fraction of a second, the train will not have moved that much, but for illustration purposes, I'm going to have the train move pretty significantly just so I can draw it. That point B is now over here. So it's, from an outside observer, the light is not going up, it's going at an angle. Right? So from an outside observer, the light is going from here to here. So actually, I'm going to draw the light in red. There'll be a red laser beam. Moving at the speed of light. And here, the light is gone like this because it's going up and sideways. So we're going to look at the distances of this right triangle. The distance from A to B is the speed of light times the time outside. And the reason it's the speed of light times the time outside is because the speed of light is the same in all reference frames. This is what the light appears to be doing. Remember, this is the speed of light times the time inside the train. And this is the velocity of the train times the time, which is only observed from outside the train. So this must be outside. So the point is we need to define variables. T is time inside the train. And T prime is time outside. So stationary observer. Sometimes this is called the rest frame energy because this is when something's relative to itself, it's at rest. So this is called the rest frame. I know from an outside observer, it appears to be moving, but the way you can remember that is that something is always at rest relative to itself. So if you're observing something moving, it's not at rest, right? So we're talking about what the train is experiencing. So when the train is at rest, right, it appears to experience a certain amount of time, or it does. And then a person outside experiences a certain amount of time. The whole point is in this Einsteinian relativity. What's constant from reference frame to reference frame is the speed of light. In Galilean relativity, it was time. Time was assumed to roll, to move constantly from one reference frame to the other. In Einsteinian relativity, that no longer is the case. And we can just see from this right triangle that the hypotenuse is greater than this leg right here. So therefore, what do we get right away? The person inside the train experiences less time than the person outside the train. Time literally is elapsing slower for them to manifest that the speed of light is the same in all reference frames. Time bows and warps. Warps just means it changes its rate. So warp just means it changes how it flows. That moving faster through space means you actually move slower through time. So how we derive the formula for that is pretty easy. We just look at this triangle again. Now, really important to remember t is inside time. T prime is outside time. Or the stationary observer. And this is called the rest time, rest frame, relative to itself. It's at rest. But I like this, just inside and outside. Inside the train, outside the train. So inside the thing that's moving, outside the stationary time, t prime. So the outside observer sees this. The inside observer sees this. Outside observer, inside observer. Outside observer, inside observer. Just sit with that. That's the beginning. Don't move on until you have that. And then the outside observer also sees the train move. And we have a nice little right triangle, Pythagorean theorem, ct prime squared equals vt prime squared plus ct squared. And we get from this, c squared t prime squared equals v t prime squared, v squared t prime squared plus c squared t squared. And what I want to do is I want to solve for t prime. So I want to subtract this over, and I'm going to divide by c squared. So I get t prime. Sorry, that's supposed to be squared. I get t prime squared minus v squared over c squared t prime squared. So I subtracted this over. And then I'm dividing by c squared equals t squared. And you might notice we're really close, where if I factor out the t and I square root, I get t prime squared equals t squared over 1 minus v squared over c squared. So here you might notice I could factor out a t prime squared, 1 minus v squared over c squared equals t squared, and then bring that over here, and I get that, and I square both sides, and I get this. And that's the formula for time dilation. Remember, t is the inside, sorry, t is the inside time of the thing that's moving. T prime is the outside from the stationary observer watching it move. So I know it's ironic that we call this rest frame, because that's because if you're inside the train, you feel that you're at rest. And if you're outside the train is moving, so the train is not at rest. So this is the outside reference frame of the thing not moving. This is inside the rest frame of the thing that is moving. So just remember, t prime is outside, t is inside the thing that's moving. Hope that repetition sort of solidifies that. That, I think, is the most confusing part, and you get it. So you get that t prime is always greater than t, which means that the person inside the train experiences less time, or anything inside the train. It doesn't have to be a person, it's just the moving object experiences less time. And we define something called gamma. And I know this was used for light, so we have to realize that letters are used for different things. This is called the relativity factor. And next, we're going to plug in numbers for velocity, remembering that the speed of light is 3 × 10⁸ meters per second. and see what this relativity factor is. Notice this relativity factor allows us to write this as t prime equals gamma times t. So if we know the relativity factor, we can figure this out. This is also going to appear in length contraction, energy, force, momentum. This relativity factor is kind of the thing you just throw into the classical equations to make it real. So I said, okay, this equation is approximate. Well, it turns out you can just put the relativity factor in intelligently, and it makes it correct. It makes it, when I say correct, just more accurate in describing what's happening. That's it for now. I'll see you guys on the other side.